see. Alrighty, my friends. See? There we go. Good, good. All right. So we have f of x equals 2x minus 4. And we need to find the domain and range. And I told you we could do it of just the square root. So we're going to look at that. So we have y equals the square root of 2x minus 4. Now, I know just quickly that this is something like that. It's more vertical because it's up 2 over 1, but whatevs. It's something in that form. We'll pretend the scale is different. That's why it's slanted, this way instead of vertical. It's the scale. Imagine it. I believe in you. All right. So what we're going to need to know for domain and range, well, the range is really easy. The moment that the graph goes flying through it, and it doesn't stop somewhere, correct? What's my range? Wow, I can't hear a word of what was said. What? Yep.
Y.
Yeah. Y such that, but not, y is an element of the reals for this one, but then for the radical graph it would be, yes, greater than or equal to 0. And then we can go 0 to infinity in interval notation. Now the domain is a little harder, but it's also one where it's crossing through, correct? So what's the important part for my domain? The x-intercept. And what's the x-intercept for this one? It's 2. And these ones are easy to find as well because x-intercept y just equals 0, and then we could solve. So we could move the 4 over, equals 2x, divide by 2, x equals 2. So we know because it's a positive slope, we're going to end up getting a graph that's going to curve that way, right? That's perfect. It's not at all, but let's pretend it would be like whatever. It's going to curve, okay? So it's going to be x such that x is greater than or equal to 2 xer in set notation, or 2 to infinity in interval. And then there lies the easiest one. Okay, b is x squared plus 2. So I know it has a vertex at 0, 2, and it's concave up. Doesn't look something like that. And if I don't draw scales, you don't know. And so it's completely accurate. So we're at 0, 2. We agree? The whole graph is above the x-axis, so I know my range isn't going to be greater than or equal to 0, correct? Because that only happens when the graph crosses through it. So what am I going to have to do to get that lowest y value? Square root the 2, because all I'm doing is I'm keeping my x's rooting my y's, right? That's what my mapping is. xy becomes x root y. So this is going to actually drop down to square root 2 instead of 2, right? And then these will all drop and you'll get a wider graph. That's all that's going to happen. So my range is going to be y such that y is greater than or equal to root 2 YR. Now, if all those y values just drop, because when you root a number that's greater than 1, they get smaller. We agree? That's what you said? If it was between 0 and 1, they got larger. So 0.5 went to 0.707. I just raised it a little bit. But all of these are actually y values that are larger than 1, correct? So the x values will stay, but my y values are going to drop. So all that ends up happening if you have a parabola that's above the x-axis is you get a wider parabola, right? Because all those y values stretch out. You just get a wider one. So what's the domain of any quadratic? I forgot. XER. Sorry, I'm correcting interval notation. That's an infinity symbol. It doesn't look like one, but it is. And that's round. All right. Domain. X such that x is an element of the reals. Or negative infinity, positive infinity. So we're looking at all different types. This one's x squared minus 4. Its x-intercepts are at x plus 2 and x minus 2. If you don't know, you could factor this one and then solve. So I get x equals negative 2 and x equals 2. So I have a graph. And then my vertex is at negative 4, 0 and negative 4, right? And then I go, choo, choo. That is not symmetrical. Pretend it is. Drawn perfectly. All right. So there's our graph. So does it cross through? Yes. Is it concave up? Yes. So does it go on for life? Yes, upwards, correct? So that whenever it crosses through the x-axis and it goes on for life upwards, it's going to be greater than or equal to 0. It's going to be your range, right? There's going to be instances like D where you're going to have a concave down graph and it's going to sandwich your y values, right? But this one, it's just going to make your y values go up. So what would happen in this case is you're going to end up having an invariant at 1, an invariant and an invariant 1. The 0.5 bumps a little up, and these are going to drop down. Say it's at 4, it'll be at 2. Ooh, at 2. So, something like that, right? So my range is going to be y such that y is greater than or equal to 0, because it keeps going on forever, because it's not sandwiched. It's not concave down. So 0 to infinity. And my domain is going to be less than -2, or less than or equal to, or greater than or equal to 2. There's no numbers in the world that can be in between those two, correct? So we can't sandwich it. So we have to go x such that x is less than or equal to -2, or x is greater than or equal to 2, XER. In interval notation, you have to do this one separate. The or symbol is just a U, it means union, and then that one separate. So we go -infinity to -2 square bracket, or square bracket 2 to infinity. Yo.
Can you use union symbol inside interval?
Yep. Set notation, so you should be able to do it. I don't think you can. I'm going to write that on a little sheet. We'll ask you ask. The reason why I don't think you can is we do set theory in 30-2. And in set theory, this little u means union, which means or. So when you do Venn diagrams, it's anything in this one or in this circle, I write down what the numbers are. So we're doing Venn diagrams in 30-2 and sets. The squiggly bracket means the set of values. And this is involved when talking about sets. So like capital A or capital B. So it wouldn't normally be involved in the actual set itself. So I'm going to ask. Got a list. I'm going to add to it. Okay. And the last one. Ooh, you'd think the train was right here. It's not. Oh my gosh, the drawing. I'm just a disaster. Okay. All right. So the last one, f of x equals -x squared plus 3. We know it's concave down. We know a vertex at 0 and 3. Okay, it's amazing. If I want x-intercepts and want to find them algebraically, I do 0 equals -x squared plus 3. Subtract my 3 over equals -x squared. Divide by -1. Or I could use quadratic formula, but when you only have a leading and a constant, you can solve them without the quadratic formula. 3 equals x squared, square root. If you take square root, you get plus or minus. So x equals plus or minus root 3, which is 1.773. Not the most accurate graph, but this is root 3, this is negative root 3, and this is 3. We agree? So my domain, what's going to happen with this graph when it's concave down? Well, when it's concave down, this is going to stay, this is going to stay, 1 is going to stay, 1 is going to stay. 0.5 is just going to bump a little up, right? At 0.7. And then 3 is going to bump down to the root of 3. We agree? So now my max is actually at root 3 as well. And now my values are sandwiched between the two values because it's concave down, correct, for domain? So my domain is going to be x such that, and now you can sandwich them. So you go low to high. Negative root 3 is less than or equal to x is less than or equal to root 3. So if you go low to high, these are actually the same direction. And the reason why they're the same direction is you are reading from the x, and that's the biggest thing I try and start teaching from grade 10 onwards, is you read from the x, which what the heck does that mean? Well, that means that x, when it's open to the x, is greater, correct? When it's close to the x, is less. So x is greater than or equal to negative root 3, and x is less than or equal to root 3. So that's why the symbols are always in the same direction, because you're reading from the x. You're not reading from left to right. So x is greater than or equal to negative root 3. X is less than or equal to root 3. If you know that when you sandwich them, it's basically two less than signs, low to high, you can get away with that too. But it's better to understand one. And then XCR. If you have a choice, interval's the easiest. Negative root 3 to root 3 square bracket. For the sandwich ones, interval's the easiest. Now my range, this is the one that gets done wrong the most, because they'll say y is greater than or equal to 0, but it's not. It is that, but it's not only that. It's greater than or equal to 0, but it's what? What's the highest y? Less than or equal to root 3, right? It's sandwiched between. It's this blue graph now. So your range is y such that 0 is less than or equal to y. I don't know what I'm writing there. Is less than or equal to root 3 because of this one. Y, bless you. So if you have a concave down parabola and some of it's above the x-axis, you'll always have sandwiched domain, and you always have sandwiched domain and range. Because your domain will squish between them, because that's you only have like the little top hill part left, and your range will squish because it'll squish down. So you sandwich between these values. Does this make sense? Going through all the different types? Okay. Then what they can do is not even give you the equation. They can just give you the graph and say, sketch the square root graph. So, in this case, if I have a graph and I sketch a new graph, I use what? Mapping. My mapping for this, from this to just the square root of a function, is always x, y becomes x root y. So basically, every single one of the negative y values is going to go away. We agree? So this part's going to go away. And if you don't believe me, I'm going to pick one. This one. Negative 4 and negative 7. So negative 4 and negative 7 is going to become, oops, I got a little ahead of myself there. It's going to become that. Negative 4 and negative 7 is going to become negative 4 and negative root 7. Holy dynamite. We'll just put a plus sign there. Negative root 7, which does not exist. Because you can't take the square root of a negative number. So all these arms just go away. Then the next thing I always do is I go to my invariant points and plot them. So my zeros, where y equals 0 and y equals 1, I just go and I plot them. Why can I do that? Because they're invariant. They do not change because the square root of 0 is 0. Square root of 1 is 1, right? The next thing I always go to is my 0.5, where my y equals 0.5, and I just draw a dot above it because it's going to go to 0.7. So here's 0.5 right here, and then I just go up, straight up from it to 0.7. So it's literally just about on the line still. 0.5, and I go up to 0.707 because the square root of 0.5 is 0.707. I'm struggling with my speaking today. And then after that, you can take any y value and literally just drop it. Drop it like it's hot. Just kidding. All right. Not even a smile. Oh, Alexa, I got a smile. Seamus just felt bad for me, so he's smiling. Okay. So we can pick all the points along here if we want to. We can go at whatever this x is and 2, right? Oops, I made it green. That's a problem. So wherever this x is and 2, so the square root of 2 is 1.4. So now instead of it being at negative 2 and whatever, and 2, it's now at negative 2 and whatever and 1.4. So it'd be like here now. Like this 2 would drop down. And you can pick the 3 and drop it down, and the 4 and drop it down. I would go to the 4. I'm going to pretend negative 2.25 and 4. I'm going to give it an approximate x. Now it's going to become negative 2.25 and root 4, which is just 2. So it's here. You see how you can sketch the whole way along if you want to? They're not going to be the most accurate x's, right? But you can still pick some. I could do -2 and 5. It's going to become -2 and √5, which is a little more than 4. I mean, a little more than 2. So it's like here. Then I could do this one, 1 and -1 and 8. And it's going to become -1 and √8, which is a little less than 3. And then this one's at 0, 9, so it's going to be at 0, 3. So you can look at, if you did actually do what I asked and you did draw these on your own, you probably gave like 3 points. Did you give a whole bunch? Good. The more points you get, looks like, yeah, no, maybe 5. You should at very minimum have 7. Because you should have the 0, the 1s, right? The 0.5s, and then at least this one dropped down to 3, at the very least, okay? Just kidding. All right. Goody, good. So then we just go. So if you look and pretend that mine was on paper and I actually went through all the dots because I'm more accurate on paper than when I'm covering it up with my hand trying to draw on it. The more points you put, the more accurate it is, right? Some people will like draw like 2. I'm going to do this in red. So they do these points, they'll do these ones and this one, and then they're just like, and I'm like, no, bad, okay? They won't give you the marks. They don't look the same, do they? Like if I were a person who saw this, I'd be like, no, okay? And I am a person. I don't know why I said if I'm a person. I am a person, and I saw it, as if like there's dogs marking it or something. I don't know. Okay, so then this one is concave up. So sorry, let's go through the domain of this one. It would be between -3 and 3, right? And my range between 0 and 3. I know it didn't ask you that. I'm just clarifying that that's how your domain would be sandwiched, because it's concave down and it was actually above. Now this one's concave up and it's above. So I'm going to plot here my 0 and my 1, my 0 and my 1. I'm going to go to my 0.5. I'm going to draw a little up. Right about here. I have to like start at 0.5 and then just make the dot bigger. And then my 0.4 is going to drop down to 2, or my 0.4. Ooh, I'm not going to talk. I'm just going to drop. Safer that way. This 4 is going to drop to 2, same x. And then 1, 7 is going to become 1 √. That's 4 and 7. It's going to become 4 and √7. And we're going to get a little something like this. Look how pretty it is. You know what dreams are made of, this graphing. Or Disneyland. Options. I think it's this. Yeah. So your domain would be x is less than or equal to -3, x is greater than or equal to 3, and your range would be greater than or equal to 0 because it goes on forever, right? And it crosses through. I should do like directing of traffic. I'd be so good at it. I just realized. Now here, example 8. Explain why the points where f of x equals 0 and f of x equals 1 are always invariant when the graph is the square root of a function. How would you explain that on a test if someone asked you to explain it? Yeah. Yeah. So you could say y equals f of x and y equals root f of x. Use the mapping of the two would be xy becomes x root y, right? That's the only thing you'd be missing, Alexa, is to state that part. And then when you'd say, hey, when I take any x value or any coordinate with a y value of 0, x and 0 would become x root 0, which is x and 0. X and 1 become x root 1, which is x and 1. I wouldn't even put a number in for x. You could do examples. You could say, okay, if there's a point that's 4 and 1 on the graph, it'll become 4 and root 1, which is 4 and 1. You can give examples at the end as well. But the best would be to describe mapping and say that, hey, when I go from y equals f of x to y equals root f of x, my mapping goes from xy to x root y. And then go from there with your explanation as to why square root of 1 and square root of 0 is still 1 and 0. Okay? I'm going to give you some questions to work on, and then at 9:30. We're going to start this next set of notes, which is the rational ones, which I handed out earlier to you. So your homework for this number 2 is, here's the coordinate. Give me the new coordinate. So no, it's not a lot. That's like rooting the y's. So I want you to do these ones, and then I want you to use, this is the last one, y equals x squared minus 3x minus 4. I want you to determine the invariant points algebraically, because they don't ask this in the test. The invariant points algebraically. I should say coordinates. So you're doing 2BC, 5, 6BC, 8BC, and then this equation, you're going to find the invariant points algebraically. If you work, this is easily accomplishable in the amount of time I gave you in class to do this. Because these two are just coordinates. Like, they're not the most extensive printing things. So work on this. So, my friends, we're carrying on. The original function that we're going to look at is the original rational function, which you dealt with rationals last year. You just didn't deal with them mainly as graphs. You kind of did in reciprocal graphs a little bit. So a reciprocal graph is when they ask you to find f or g of x, let's say, and it's 1 over f of x. So you take whatever f of x is and you slide it underneath the number 1. So you make it the denominator. So that's a reciprocal graph, taking an original and then sliding it underneath as your denominator. Just like we did with the radical graph, we slid it underneath the square root symbol. Rational graphs, you are given a function that is something over something already. So you're not transforming a linear or a quadratic into an actual function. You're given a rational function. So reciprocal graphs are rational graphs, but they're transformed from an original function to a reciprocal. So basically with reciprocal graphs, all that happened is all your x's stayed the same. If you did mapping, your mapping would be xy becomes x comma 1 over x, or 1 over y, sorry. All your y's go put under 1. So here, can you type in 1 over x into your calculators? And I'm going to make the volume of my calculator now. 1 divided by x.
Oh, right, this is the one with the asymptotes.
Yes. Good old asymptotes. It's like a fidget spinner. I've never heard that before. But yeah. So we're going to do 1 divided by x. Now remember, if you go 1 divided by x in these fancy calculators, and you go to the table values, it will give it to you in decimals, correct? If in the fancy calculators, you use alpha y equals enter, and you do 1 over x, it gives it to you in fractions. Okay? Fancy calculator. If you don't have the fancy calculators, you need to put them in brackets, right? So, we have 1 over x graph. Boom. Look at that baby. I'm going to go zoom 6 so we can actually look at it. Now, if you have the older calculators, your calculators in the olden times, and I can say olden times because if you have the TI-83s, the first year that they were used in Saskatchewan was when I was in grade 11. You're welcome. In the olden times, I was the first year of the TI-83. In the olden times, the calculators thought that they needed to be continuous. They were like, everything must be continuous graphs. But these are not continuous graphs, because actually, we got ourselves some little asymptotes running along here. little horizontal one, little vertical one. But the old calculators are like, must not be a broken up graph, must be continuous. So what they do in these older calculators is they go like this, and then they connect it up here and they run it. This doesn't exist, okay? And it will tell you in your calculator that it doesn't exist, but in some of the older calculators, it'll try and force it to exist. Like it'll draw it so it connects it. It must have been like a problem, a defect in the actual programming of that calculator. It'll force them always to connect, even though it's not a continuous function. It'll make it continuous. But if you went to like second table, it'll actually say there's an error there. So it won't like show that it's actually continuous on the table because it isn't continuous on the graph, but it'll force it to connect. All right. When I put in, now look at here, it looks like it stops, doesn't it? It doesn't. It runs really, really, really close. So these will keep going on for life. This graph's going to keep going out this way, and then it's going to run straight down here. And I always refer to it as a rural farm girl, as this is an electric fence, okay? These are little zapping electric fences. So here's an electric fence, boom, 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 boom. And you're like, why do you have electric fence, you crazy person? Because we have cows, and cows like to go where there's grass. And where is there grass, the most of it? In a ditch. And where do you not want your cows? In a ditch. Because what are they going to do? They're going to go on the road. What's going to happen? Someone's going to hit your cow dead, lose money. Okay? So, pardon? Well, you're not the person. The person isn't trying to eat out of the ditch and then crossing on the road. So we're not as big of a problem.
Have you ever
Yes.
My cousins used to grab the electric fence and then they would grab me.
Well, there's,
They would,
it
they
goes
would,
through.
like, run over the one
It's not, I
person,
wouldn't suggest.
grab you, and then they would give it to the other older one. And then they would-
Yeah, and it's not like extremely like crazy. Like they don't turn. You can turn it up or down on an electric fence. You don't make it like. Don't make the cow like jump 20 feet back or anything. It's just enough that it's like the cow just touched it. And it's like, oh, not today. But anyways, if you ever drive by cows, you'll notice this. Their heads will be shoved through the fence that's not an electric fence, because they wouldn't do it if it was electric, and they'll be eating the grass in the ditch because it's really tall grass, and where they're standing is like really short grass. And where do they go? They go there. So anyways, put yourself an electric fence there, right? So what's the cow going to do? It's going to, if you're a cow, here's the cow. The cow is going to be in the middle here. I made it have ears like a cat. Anyways, it's a cow. And it's going to come along here and it's going to be like, ooh, there's grass over here. And it's going to come along and it's going to be like, electric fence, electric fence, electric fence, electric fence, electric fence. I'm hoping there's a break in the fence. Electric fence, boom. And it's like, no, there wasn't one. So then the cow comes back and it's like, electric fence, electric fence, electric fence, electric fence. Can I cross it? Nope, 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 boom. And then you have a rational graph. And then there's a cow on this side who's like, maybe there's an opening here. And then it walks across, so it's like, ooh, electric fence, you get the point. And then electric fence, and then it keeps going on for life. So when you guys think that it stops and you give me some crazy stuff, that cow is not going to stop. It is going to keep going and hope for some openings. But it's not. It's not going to have an opening because those are electric fence, these little dashed asymptotes that exist.
Do they always go on then, like with any kind of function like this?
Yes. So, get rid of my cattle drawing. Okay, so we have this, and it keeps going. And when you go to sketch it, you're going to sketch the blue to keep going with arrows, correct? And then you're going to sketch a dashed line to represent with arrows the asymptotes. So you always draw the asymptotes on as a dashed line, because they don't exist, right? Anyways, so if we put in the 10, which I told you guys to do for y2, do 10 divided by x. What happens to my graph? It goes further. The red is the new. Nope, that's asymptotes. They still have the same asymptotes. This cow just took a longer trip to get there. They're like, yeah, I know there's no fence there, so I'm going to just go a little wide. But eventually, this cow is still going to get closer, because if I go like this, I'll show you. So if I go to my window and I make my y minimum be like -50, let's say, you're going to see that the cow actually does approach the fence eventually, right? They're still going to approach that. They just sometimes take a different route. Now, if we have, second table, if we look here, I have -3. This is my original. That's the parent function. 1 over x is the parent function of a rational. Now I did 10 over x. What happened to my y? It was negative 1/3. It's now negative 10/3. What did I do? Times it by 10. Let's check. It was negative 1/2. Now I have negative 5. Negative 10 times negative 1/2 is negative 5. Negative 1 times 10. Negative 10. So if you look here, what's happening? All my y's are being multiplied by 10. Why would that be? Transformation experts. People with big brains.
Because it's a 10, and the other one was a 1.
It's a 10, the other one was a 1. Good suggestions, good suggestions. Yes, yes, true, true. Yeah.
Yeah, from 1 over x to 10 over x, you need to multiply 10 over.
Yes, so, yes. Okay, so, what Colin said, which is very true, is that if we have y equals 1 over x, and we go to y equals 10 over x, that could be rewritten as 10 times 1 over x, couldn't it? Could it not? What is the number in front of a transformation? What is it? What kind of transformation is it? A what stretch? Big brains. Vertical stretch by a factor of 10 about the? So this one has a vertical stretch by a factor of 10 about the x-axis. What would the mapping be? Look at that unison. Perfective. If I did replacement, how would I replace that? Remember when you replace the variable, so I'm going to have to replace it in for the y. Not 10y. Y becomes 1 over 10. Y. Because you have to replace it into the y, then you have to multiply it over as a 10. So replacement notation doesn't come up a lot, but I just want you to be able to know what it is. It's replacing it in for the actual variable. So if I want there to be a 10 on this side, I'd have to replace it with 1 over 10. Because how do I move the 1 over 10? I would multiply, this would be 1 over 10y, so I'd multiply by 10 and move it over here. Yeah.
Did you replacement notation for x too?
Yeah. Yeah. Replacement notation for x is always flipped, right? So for y, it would be the same thing because you're with the y and then you move it over. Yeah. Okay, let's look here. The graph for a rational function of the form y equals a over x represents a vertical stretch by a factor of a the graph of y equals 1 over x. Because y equals a over x can be written as a 1 over x. Graphs of the rational function of the form of y equals a over x have separate branches that approach the vertical asymptotes x equals 0 and the horizontal asymptotes y equals 0. So your parent function, let's go back to this one, up here. This is my parent function. We had it drawn. Let's go back here. I'm going to clear this one out. I'm going to go zoom 6. So that's my parent function, right? It's drawn down here and down here. If we have a reflection in the x or reflection in the y, what's going to happen? It's going to flip quadrants, correct? So this is quadrant 1 and 3, because remember we go counterclockwise, 1, 2, 3, 4. It's in quadrants 1 and 3 if it's positive, but if it's negative, it's actually going to move it to 2 and 4. Because if I reflect in the x, this one's going to move down, this one's going to move up. If I reflect in the y, this one's going to move over, this one's going to, so it's going to just flip-flop. Whether it's in the x or in the y, it's going to move to quadrants 2 and 4. So what is my domain of this? You're going to write it in the parent function on your notes right here, but I'm going to write it on the graph because we're going to see it. So, we have an asymptote running here, which is the y-axis. The y-axis is what equation? X equals 0. And then this one is the x-axis, which is what equation? Which one of these is horizontal? So the horizontal asymptote, see that happening? The horizontal asymptote is going to be at y equals 0. And then the vertical asymptote is always an x equals asymptote. So the vertical asymptote is going to be at x equals 0. What's the only thing that can move those? What kind of transformation? the translation. So the only thing that actually can move an asymptote is a horizontal translation can move the vertical, and a vertical translation can move the horizontal up and down, right? What's the domain and range of this? Yeah, x such that x cannot equal 0, XER. In set notation, you literally have to list the number line from negative infinity to 0, and then 0 to infinity. So you'd actually have to, because it's basically this. And you're representing a number line when you do interval, right? So you'd have to, if they asked for it in intervals, we'd have to go negative infinity to 0, round bracket, because it can't equal it, or 0 to infinity, round bracket. If they said set notation, we do the top. If they said interval, you do the bottom. And my range for this one, y such that y cannot equal 0, YER, and the interval notation is going to look the exact same because you don't actually put variables. Right? Now, what is the vertical stretch? The one where it was 10 over x. Did it affect my domain and range? No, because my domain and range is only going to change if I have translations, because the translations will shift my vertical asymptote and my horizontal asymptote, right? So unless you have translations, your domain and range are going to always be these. Okay? And that leads us into tomorrow.